Hello and welcome to part one, of the chapter two lecture on molecular representations. Okay, so we want to be aware that there are multiple ways to represent molecules. The simplest way would be the molecular formula, which is shown over here, C3H8O. That is the fastest way to represent a molecule, but it doesn't give us any information about how these atoms are bonded together. Then we have what's called a condensed structure. This gives us a little more information about how things are bonded. So this shows us that the hydrogen is bonded to an oxygen, which is going to be bonded to the next carbon over. This carbon will have a hydrogen bonded to it, as well as the following two carbons. And then these carbons will each have 3 hydrogens attached. So it takes some getting used to understanding the condensed structure, but it is still a fairly simple way of representing structure, which is really helpful. Then we have what might be called a partially condensed structure. This gives us a little more information about how things are bonded together. It's a little more visually easy to see, while still not showing every single bond. So for example, it's not showing the bonds between this carbon and the 3 hydrogens attached, as well as this carbon and the 3 hydrogens attached, and then the oxygen bonded to this hydrogen. And then we have the full Lewis structure, which shows every single bond between every single atom. And both of these can also optionally have lone pairs. Sometimes you'll see them without lone pairs, and that's because they're implied. If you see an oxygen without lone pairs that's making 2 bonds, then the chemist knows there's also 2 lone pairs such that that oxygen has an octet. So while there's multiple ways to represent molecules, some show the structure much more clearly but are more time consuming to draw, and then others are not as descriptive but much easier to draw. So let's look at some different compounds that can be made using this molecular formula. So you can see there's 3 compounds here: isopropanol, propanol, and ethyl methyl ether. If you were to carefully look at the molecular formula for all 3 compounds, you'll notice that they're all C3H8O. So if you just write C3H8O, it's not clear which of these compounds, for example, you might be talking about. That's why we need to use some of these other types of representation to make it more clear exactly which compound we're talking about. And in this case, it would seem like isopropanol was the compound being discussed. If you think about what is the relationship between these compounds? Well, if they all have the same molecular formula, but they have their atoms connected in a different arrangement or order, then they would be defined as constitutional isomers. So you're going to be looking at an activity where you're going to be asked to draw several constitutional isomers. So one thing that can really help you figure out how to do that is to think about switching groups. So for example, if you think about starting from isopropanol, how would we get to propanol? Well, we've switched where the OH group is attached. In this case, it's attached to the center carbon. We've just moved it over here to one of the N carbons and then replaced the hydrogen that was attached there back to the central carbon. So you can think about like taking either one atom that's attached and moving it around to another position, or multiple atoms attached and moving it around. So switching around the way that the atoms are bonded together. Another way is to think about, well, what if I just take this oxygen? I know that it's going to have 2 lone pairs and make 2 bonds. What if I just, instead of having it at the end, insert it into between 2 carbons? That's also possible, and that's how you would get ethyl methyl ether. So these are different ways you can think about changing the way that things are bonded to make different constitutional isomers. You do want to be really careful, however, that you actually make a different compound. So for example, if I decided to take this OH group and move it to the other terminal carbon and replace it with the hydrogen, switch those two essentially, I would end up with an OH group at a terminal carbon, and it's as if I just took that molecule and flipped it over. That's not a different compound. We want to make sure that we are actually not just drawing it a different way, but it's still the same thing with the same atoms attached. But we're actually generating a different arrangement of the atoms. And you can't just rotate the molecule around to make it equal to the one you just drew. Another really important strategy for helping to draw constitutional isomers is to calculate what's called the units of unsaturation. And to calculate the units of unsaturation, also known as the hydrogen deficiency index, you start with a molecular formula. So if you are just given a molecular formula, you can take that formula, do this calculation, and get some really helpful information from that. It will give you information about whether or not there's any rings or pi bonds present in the structure. So if you, for example, get a calculation that equals 0, you're going to find out there's no pi bonds and no rings. That's really helpful information when you're trying to figure out how many constitutional isomers can I draw. I can just say, okay, I'm not going to make any rings and I'm not going to have any sort of pi bonds in my structure. That's really helpful information. So let's go ahead and talk about units of unsaturation by starting with, what does the term unsaturation mean? Well, to understand that, we have to start with the idea of a saturated hydrocarbon. So the word hydrocarbon comes from the fact that the molecule only contains hydrogen and carbon. So if you have a hydrocarbon and it matches this formula below, C to the n, H to the 2n plus 2, where this is any integer, a positive integer like 1 carbon, 2 carbons, 3 carbons, right? If the hydrocarbon is saturated, then it will have 2 more than twice the number of carbons in terms of its hydrogen atoms. So if the formula doesn't match that, let's say instead of C4H10, which would match, what if it was C4H8, right? Or C4H6? Then we know that the number of hydrogens is not the maximal number of hydrogens that can fit on a certain number of carbons. And we say that that hydrocarbon is now unsaturated. It is not saturated with as many hydrogens as possible. Instead, it has fewer hydrogens that are technically possible, and it's unsaturated. So let's look at some examples of unsaturated compounds. An unsaturated compound as a will correspond to a pi bond or a ring. Let's look at some formulas here. So we have C5H12. You'll notice that this saturated hydrocarbon has 2 more than 2 times the number of carbons in terms of its number of hydrogen atoms. When you introduce a pi bond, you end up with 2 fewer hydrogens than would be possible if it was saturated. If you introduce 2 pi bonds, then you now have 4 fewer hydrogens than it would be possible if it was saturated. So both of these compounds that have 1 or more pi bonds are considered to be unsaturated. And when we do our calculation, we will get a number for the HDI, or the hydrogen deficiency index, that is either 0 in the case of the saturated hydrocarbon, 1 if there's 1 pi bond or ring, and then 2 if there's 2 pi bonds, 2 rings, or any combination thereof. So let's look at some isomers. And when it says isomers, it's talking about constitutional isomers. Look at some isomers of the formula C4H6. You can tell this is not a saturated hydrocarbon. Because if it was saturated, there would be more than two times the number of carbons in terms of its hydrogen atoms, so there would be 10. So because there's only 6, there's 4 fewer hydrogens and 2 units of unsaturation, or an HDI calculation of 2, which means that there's either 2 double bonds, perhaps 1 triple bond, and that's because each double bond is 1 pi bond, and a triple bond has 2 pi bonds. There could be 2 rings, or 1 ring and 1 pi bond, also known as a double bond. So these are all possible structures for constitutional isomers given this molecular formula. And it would be really helpful to plug this into a calculation to figure out, oh, okay, I have an HDI of 2. So I know I have one of these 4 possibilities. In the calculation, it takes into account other compounds that are not just hydrocarbons. For example, what if there is a halogen in the structure? Well, it turns out that a halogen is treated as if it were a hydrogen atom. Because remember that halogens only bond once and are therefore at the periphery of compounds, just like hydrogen atoms. So they're sort of indistinguishable. Also, an oxygen atom does not affect the HDI. You'll notice that the number of oxygens is not included in the calculation. And that's because it essentially can get inserted without changing anything in terms of how many double bonds or rings there are. What about a nitrogen atom? Well, a nitrogen atom increases the number of expected hydrogen atoms by 1. And that's because a nitrogen atom typically will make 3 bonds with 1 lone pair. And so when you insert it, we've expanded the number of expected hydrogen atoms by 1 compared to an alkane. So when you think about nitrogens, oxygens, and halogens, which are the common atoms attached to carbon in organic compounds, you'll find all of those in here in the HDI formula except for the oxygen atom. So we can use this formula. The hydrogen deficiency index is equal to 1/2, 2 times the number of carbon plus 2, plus the number of nitrogen, minus the number of hydrogens, and minus the number of halogens. The HDI calculation will give you an answer of 0 or a positive integer, such as 1, 2, 3, 4, etc. If you get a fraction or a negative number, you did not calculate it correctly. Calculating the HDI can be very useful. Like I was talking about before, if the HDI is equal to 0, we know the molecule cannot have any rings, any pi bonds, which means that there's no double bond or triple bond possible. That really takes a lot of possibilities out of the mix and will help us focus on what type of compounds to draw. So let's do some. First, I want you to look at this compound and predict the HDI value by just simply counting up the number of pi bonds and rings that you see. Then determine the molecular formula of the compound. So just go C something, H something, how many nitrogens, how many oxygens, how many halogens, right? So determine the molecular formula. Plug it into this equation to calculate your HDI and see if it matches your prediction. Go ahead and pause now and work on that, and then come back and we'll go over it. Okay, let's go ahead and go over how to do this problem. So first, it wanted us to predict the HDI by just counting up pi bonds and rings. I see 1 pi bond here, second one here, third, fourth, and 1 ring. So I'm predicting an HDI of 5 because I saw 4 pi bonds and 1 ring in the structure. The next thing it said is to figure out the molecular formula. We typically write the number of carbons first. We're very carbon focused in organic chemistry. So 1, 2, 3, 4, 5, 6, 7, 8. Next, the number of hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. Next, we do nitrogen, oxygens, halogens. So there's 1 nitrogen. You can write 1 or just leave it blank, and the 1 would be in 5. Oxygens, there are 2. And halogens, there's 1 chlorine, so there's 1. Next, we can take this molecular formula and plug it in to this equation. So we have the HGI is equal to 1/2, 2 times the number of carbon. Well, there's 8 carbons, so that will be 16 plus 2. There's 1 nitrogen, so plus 1. Subtract the number of hydrogen, so minus 8, and minus the number of halogens, minus 1. Notice that the oxygen number didn't matter. It doesn't go into the equation because it doesn't change the HDI. So we have 18, 19 minus 9 would be 10, right? 1/2 of 10 is equal to 5. So it did match our prediction. So calculating the HGI when only given the molecular formula is really helpful to figuring out what's possible in terms of a compound. Because if I see a compound that doesn't have an HGI of 5, I know it can't possibly match this formula. Okay, we're going to move on to the next section of chapter 2, which is called bond line structures. And I'll commonly just call this line structures. So Lewis structures, which are the way that I've been teaching you to draw structures up to this point, are helpful, but they're a bit impractical when the compound gets really large. Think about having to draw out the Lewis structure of amoxicillin. It's very large and it would be very time consuming to draw. Because of that, organic chemists are a bit too lazy to draw that out. So we need a way to draw this that gives us just as much information as a Lewis structure, but that's faster and easier to draw, and give us all the information about its size and shape. So we can't just use a molecular formula. So instead, we're going to learn how to draw what's called a bond line structure. And this is the bond line structure for amoxicillin. So it's going to be a lot easier to draw, but it still has all the information if you know how to read it. So what does it mean, right? So basically, we've omitted C's for carbons. We don't draw in C's for carbons. And that's just because there's so many of them that it's just too time consuming to draw. Instead, we just draw the bonds between the carbons and omit the C's and just know that at any intersection of 2 lines, there is a carbon there, unless it mentions that there's another atom. So we still draw in all what we call heteroatoms or different atoms, meaning different than carbon. So we'll still draw in nitrogens, oxygens, halogens, sulfur atoms, for example, because we want to make sure that it's understood that it's not a carbon between these 2 carbons. Instead, each of these 2 carbons is bonded to a sulfur instead. Also, all of the hydrogens that are attached to carbon are also omitted. It's just too time consuming to draw those in. We do still draw in hydrogens that are attached to heteroatoms, meaning all of the hydrogens that are attached to non-carbon atoms are still drawn in. So when you see an intersection between 2 lines, not only is there a carbon here, but that carbon has to have 4 bonds. So there's also an additional hydrogen bonded to this carbon, such that this carbon will have a total of 4 bonds. We can see 3 bonds already, but the 4th bond is implied, not drawn in. Another thing that's sometimes left out, specifically when we're drawing the Hecule type of bond line structure are lone pairs. Lone pairs are drawn in sometimes and not other times. And again, it's just faster if we don't have to draw them. So sometimes they're not drawn in. However, a chemist has to know that they're there. Well, how do you know that they're there if they're not drawn in? Well, one thing we know is that all second row elements need to have an octet. So that means that if I've only drawn 3 bonds to nitrogen, that would only be 6 electrons surrounding it. But we know that it has an octet, otherwise it wouldn't be neutral and stable. So that means that it also has an additional lone pair to make up its complete octet. Let's look at this sulfur, for example. It's only making 2 bonds that we can see. But again, it has to have an octet. So just like oxygen, it will also have 2 lone pairs to complete its octet. So even if you don't see the lone pairs, you should still know that they're there. One other thing I'll point out is at the end of a line where you don't see anything, this is still a carbon atom. So it's implied that there's a carbon atom here with 3 hydrogens attached. So bond line structures are really going to be the way we represent structures from now till the end of when you're learning organic chemistry. We call them the benchmark representations because they're the most important and representation that we'll use from now on. So it is really going to be critical for you to know how to draw these structures, and when you see them, to know what they imply, to know where the carbon atoms are, to know where the hydrogen atoms that are not drawn in are, and to know where the lone pairs are. It will be really difficult for you to succeed in this course without understanding how to draw these structures. So do spend some time practicing drawing them. So what is represented with all of these lines, right? The lines are bonds, and each corner or endpoint, so this would be a corner, this would be an endpoint, is a carbon atom. And then there's enough hydrogen atoms attached to each carbon atom such that all carbon atoms will have 4 bonds. Is it possible for carbon not to make 4 bonds? Yes, it can make fewer than 4 bonds, but when it does so, it has a charge, which would need to be represented on the structure. So if you don't see a charge, it can be assumed that each carbon has 4 bonds. What about double bonds? Double bonds are drawn in to the structure. They can be drawn in between any 2 atoms, like for example, the carbon at 2 and 3 in this second structure. We can also draw triple bonds between 2 carbons. If we draw a triple bond, however, we need to show the most optimal geometry. Specifically, these 2 carbons at carbon 2 and carbon 3 in butene are sp hybridized. Recall that the ideal geometry for an sp hybridized compound is linear, or 180 degrees. So it wouldn't make sense to bend, right, the line from here. And instead, because it's 180 degrees, we just continue through a triple bond in a linear fashion. If we were going to continue the chain and there wasn't another triple bond, we could start bending the carbons in a zigzag formation from that point, but we don't bend at an sp hybridized carbon. So another skill that you need is to be able to know how many and the location of hydrogen atoms in a molecule. So for example, you may recognize by now that this is a carbon atom at this particular bend or intersection between these carbons that are attached to it. But additionally, you need to know that because the carbon makes 4 bonds and only 2 are shown to the 2 other carbon atoms, that there must additionally be 2 bonds to hydrogen atoms that are just not drawn in. So let's do some practice. You want to practice identifying the location of the carbons and the hydrogens in a skeletal structure. So in your mind's eye, you should see the hydrogens and where they're located. Let's go ahead and take some time to practice How many carbon atoms and where are they located? How many hydrogen atoms and where are they located? And when you get down to this one, go ahead and redraw it as the Lewis structure. It would be best if you paused at this time, practiced, and then continued on when you're ready. Okay, hopefully you have worked on this the best of your ability. Now, the first thing we can do is go ahead and draw in carbon atoms. So remember, they're at the endpoints and the intersections indicated with the bonds or lines that you see. So I'm just go ahead and draw in all the carbons on these 3 hydrocarbons up top. What about the hydrogen atoms? How many are there? Where are they located? So this carbon is making 1 bond to another carbon, which means that it also has to have 3 hydrogens attached. Each of these center ones will have 2 hydrogens attached because they each are making 2 bonds to other carbons. But any on the end will have 3 hydrogens attached. So I can just go through this and draw in all the hydrogen atoms. You can see as I'm doing this that it's a bit of a time-consuming process. That's why organic chemists don't do it very often, if they can avoid it, because it's a little bit laborious. I'll go ahead and finish this though, so you can compare what you drew. One thing you might have noticed as you finish this is that actually all 3 of these compounds are constitutional isomers. They all have the same molecular formula, but different atom connectivity. What is their molecular formula? Well, they're all C6, and they're all saturated hydrocarbons. So without even counting, I know that there's 14 hydrogens attached to each. Okay, so let's look at this structure. Right? Let's go ahead and put in all the carbons. So there's one here, 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 here. Right? And then all the hydrogens. Remember that this one is shown because it's attached to sulfur. So should I put any here? The answer is no, because this carbon is already making 4 bonds. That means it doesn't have any hydrogens attached. I'll just try to erase that. So be careful not to add too many bonds to the carbons. Some of them already have 4 bonds and don't need any additional bonds. You can see how much work it would be. Go ahead and draw this out as a Lewis structure. Let's go ahead and do the molecular formula. How many carbons? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. How many hydrogens? Don't forget the one that's drawn in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. No nitrogens, no oxygens, 1 sulfur and 1 chlorine. You can do sulfur and chlorine. Hopefully you got the same thing that I did. Okay, let's keep going. So let's talk about the specific rules involved in drawing bond line structures. So the first rule is sp2 and sp3 hybridized atoms in a straight chain should be drawn in a zigzag format. So with 4 carbons in a row, we would draw a zigzag just like this, which implies 1, 2, 3, 4 carbons in a row. When drawing double bonds, draw all bonds as far apart as possible. So we're still trying to take into account VSEPR, right, which says that electron groups repel each other and they want to get as far away from each other as possible. So this kind of implies a very small bond angle between this carbon-carbon oxygen. It implies that it's something like 60 degrees. But we know that this carbon is sp2 hybridized because it has a steric number of 3 with 3 atoms attached and no lone pairs, or 3 sigma bonds and no lone pairs. So the angle is going to be 120 degrees and the molecular geometry will be trigonal planar. So it's much better to draw this, which more correctly implies the correct angle than something like this. Be careful when you're drawing single bonds that you don't think it makes a different molecule if you draw the zigzag going one direction or the other direction, right? These two things are the same. It doesn't matter that this carbon is sort of drawn up here versus down here, right? All of these single bonds have free rotation. If I just rotate around this, I'm going to end up with that. So I haven't actually drawn a different compound. So another way to do it is to count the carbons or label them with numbers. 1, 2, 3, 4, 5, where there's a branch at carbon number 3. That's the same here if I was to count 1, 2, 3, 4, 5 with one branch or one carbon at number 3. So just be careful that you're not thinking that they're different when they're actually the same, just drawn with a different bond rotation. Rule number 4, all heteroatoms, heteroatoms means an atom other than carbon and hydrogen, must be drawn as well as the hydrogen atoms attached to them. So it's really nice that we get to omit the hydrogens attached to the carbon atoms, but we still need to draw in any hydrogens attached to any non-carbon atom. So those need to be drawn in just like you would see here. You could draw a line to the H, a bond, right? Or just write OH. This is kind of like a partially condensed structure as opposed to a fully drawn out structure where you include the line or bond between the oxygen and hydrogen. Both are acceptable. And then rule number 5, which is the cardinal rule, which means that, it's the most important, cannot ever be broken, right? No exceptions. Never draw more than 4 bonds to a carbon atom, right? So recall the octet rule for second row elements. We cannot exceed the octet for second row elements. So that means carbon can never, ever make more than 4 bonds. So make sure you don't draw that. Okay, let's talk about identifying what are called functional groups. So line structures make it easier to see when there's a change in the bonding in a particular chemical reaction. So for example, if I asked you to look at this and said that, okay, this is the reactant and this is the product, right? You might kind of somewhat easily see that this isn't drawn anymore, but it's a little hard to see what exactly has happened in this reaction. Look at this line structure. It's much clearer that the double bond has been removed, right, in going to the product of this particular reaction. It's much easier to see changes in structures during reactions when we draw line structures. So that's an advantage for drawing line structures. Let's talk a little bit more about that term that I just used, functional groups. What does that mean, right? Well, functional groups are groups of atoms that are bonded together in a certain way, right, with a specific arrangement, such that they undergo specific chemical reactions. So they're like parts of molecules with a specific bonding pattern that we can just study how those react once and apply it to any structure that has that particular arrangement of atoms. So it's really useful to recognize functional groups because you go, okay, I see this alkyne. If I study how alkynes react, then I'll know how other alkynes that are not exactly one butene might react, because all alkynes have similar reactivity. Right? So that's why we're learning these functional groups. The book is organized into reactions by functional groups. So we'll start with a functional group called alkyl halides, which actually didn't make it on this picture. But I'm about to go over all the functional groups. Not all of them, but the ones that are the most important for you to learn now. There are actually more than you're introduced to initially, but we're just going to learn the most important ones. Right? And then we go on to reactions of alkenes, reactions of alkynes, reactions of alcohols, reactions of ethers. These are all different functional groups. So the book is really organized by reactions according to functional group. So you will be learning about and reviewing all these functional groups as we go through the entire year of organic chemistry. Okay, I like to just take a minute actually and draw out some functional groups, just because it's kind of nice to see it drawn out as opposed to just stare at a picture. So let's go ahead and do that. And we can sort of group them or organize them according to ones that are fairly similar. And that might also help you learn them. Okay, so let's go ahead and start off with I'm going to start off with just drawing a structure. Right, so this is a saturated hydrocarbon. Again, sometimes I put something else in there. Okay, so this is a saturated hydrocarbon. We actually are going to call this alkene. However, alkenes are not a functional group. This is said to have no functional group, which is a little bit strange, but I want to make sure that you understand that hydrocarbons that are saturated have no functional group. Even though they're called an alkene, that's not actually a functional group. Don't shoot the messenger. That's just the rules of how it works. Okay, so I am going to start introducing functional groups too. Right? The alkene and the alkyne are similar. These both actually count as functional groups. So what would those look like? So anything where you have a carbon-carbon double bond. And I'm drawing line structures now, right? Because again, we need to transition fairly quickly into thinking about and looking at structures when they're drawn in that benchmark representation, the bond line structure. Right? So anytime you have a carbon-carbon double bond, that is called an alkene. And a carbon-carbon triple bond is called an alkyne. And it doesn't matter if there's a hydrogen here at the end attached to this carbon, or if it continues right into another carbon. As long as you have a carbon-carbon triple bond, you have an alkyne. So these are actual functional groups. And I'm going to kind of use different colors just because I think it's going to be easier to remember. Colors really actually help memory, right? Visualize differences. Okay, let's keep going with a alkyl halide. So anytime you have a carbon attached to a halogen, and it could be a chlorine, it could be a bromine, fluorine, iodine, any of the halogens. Okay, so if you have any carbon attached to a halogen, then we're going to call this an alkyl halide. We're being very specific here because it could be any halogen. Now let's do a similar one here. Let's do, what if we had a structure like this? This seems like it's going to be an alkyl halide because there's a carbon attached to a halogen. However, we also have the carbon that's attached to the halogen is also attached, double bonded to an oxygen. That actually makes it a different functional group. This is no longer an alkyl halide because of this double bond to the oxygen. Instead, we now call this an acyl halide. The reason why it's a different functional group is because it reacts differently than alkyl halide, so we need to call it something different. Okay, let's go on and look at another set of compounds. How about next we can look at ones that involve oxygen? Maybe we have a carbon attached to an OH group. Okay, so you might see OH somewhere, any carbon attached to the OH group. Right? This is going to be called an alcohol. Really underline anything that is a functional group name. Right? So that's an alcohol, but let's do some that are kind of similar to that. What if we have that carbon that's attached to the OH group is also attached to an oxygen or double bonded to an oxygen? This is no longer an alcohol. This is actually now called a carboxylic acid. So it might help if you make some flashcards to learn these different functional groups. Okay, so those are kind of let's look at another one that's really similar. We're going to do, what if there's a carbon double bonded to an oxygen, bonded to an oxygen, so it's very similar to the carboxylic acid, but is now bonded to another carbon. So instead of an OH, we have what we call an OR, R being like any carbon-based group. So this is actually called an ester. Okay, so that's a little bit different. And this is not like the person, the name Esther, E-S-T-H-E-R. There is no H. That's just something to be aware of. Let's look at some other functional groups that have this carbon double bonded to oxygen. That's actually very common in different functional groups. What if we have a carbon double bonded to an oxygen with two carbons on either side? Right? This would actually be called a ketone, no Y. Ketone. Very similar to a ketone, but where the carbon bonded to the double bonded to the oxygen is now only bonded on one side to a carbon, on the other side to a hydrogen. This is, by the way, an exception. This is one time when we will draw in a hydrogen attached to a carbon. Normally that's omitted in a line structure. And in this case, we draw it in just because we don't want somebody to think, oh, we accidentally forgot to draw it and we meant to draw a ketone or something. So now this is called an aldehyde. Okay, one more over here that's kind of similar to an ester. Maybe you could think of it as kind of similar to, I guess it's the most similar, I would say, to an ester. And it's not a very common one, but it is one that we do learn at the outset of the course. What if you see two carbons double bonded to oxygens, and in the center, they're both bonded to the same oxygen? This is actually called an anhydride. I'm going to put it next to this one so you can see the difference. So it's really important that you understand that this is not both an ester and an anhydride. Because of the additional carbon double bonded to an oxygen, it's now just, the whole thing is just called an anhydride, and there's no ester present. So hopefully that makes some sense. Okay, I am going to throw in here a random one. very different from all the others, right? Just to kind of mix it up. When you see a 6-member ring with 6 carbons, all in the ring, and then these alternating double bonds, and they can be here, here, and here, or here, here, and here. Okay, this one is actually called an aromatic. It's kind of all on its own, different than all the others. Okay, let's look at some ones that involve nitrogen. Nitrogen is also a very common functional group. So what if we have carbons that are attached to a nitrogen, and that could be attached to hydrogens. Maybe it's attached to 2 hydrogens. Maybe it's attached to 1 hydrogen and it has 2 carbons attached to it. Maybe it's a nitrogen with 3 carbons attached to it and no hydrogens. Right? All of these are considered amines. They're all an amine. The fact that I forgot to underline these ruins my OCD, so I have to come back. Okay. What is very similar then to an amine, but not an amine? Let's talk about that. So we have, very similar would be a structure where there's a nitrogen, but next to the nitrogen, the carbon attached also has a CO double bond. Right? And again, this could have 2 hydrogens. It could have only 1 hydrogen, right? And it could have no hydrogens attached to the nitrogen, just like the amine. But if it's got that CO double bond right next to it, then it's no longer called an amine. And it's called, now different people pronounce this differently. So some people might call it an amide, right? I call it an amide. It can be a little confusing because there's something called an imide that's very similar, like IMIED. This is amide, should be a little different in the way you say it. But sometimes, again, it's called an amide. So you can see it different ways. Hopefully you're not too confused by that. Okay, so I think I might have hopefully hit all the major functional groups here. And let's go ahead and just take a look in the book, just to make sure I didn't forget it. Because I'm just doing this from my memory. All right. Oh, I did forget one. Actually forgot a couple. You do a very good job today. Okay, 3 more. So, forgot some major ones, so I'm glad I checked. So we have one more thing. What if there's an oxygen in between 2 carbons? Right, so maybe it could be, any carbon-based group on either side. No hydrogen directly attached to that oxygen. This would be called an ether, right? So when you see OH, that's an alcohol. But if there's isn't a hydrogen directly attached, and instead carbons on both sides, that is an ether. Not to be confused with an ester, and it's similar. And then the only other 2 that are included, they're not super common, which kind of explains why I forgot them. But they are included in the initial 20 that you're supposed to learn in Klein, are the sulfur-based ones. So what if there's a sulfur instead of an oxygen, instead of an OH and SH, right? Or a sulfur in between 2 carbons, right? Those are the last 2 possibilities. Sulfur is kind of like oxygen. It's right below oxygen on the periodic table, so it reacts similarly. So anyway, this one is called a thiol, kind of like an alcohol. Helps you remember it. They both have the "al." And then this one is called a sulfide. All right, that should be it. And hopefully you can make some flashcards and then learn those as quickly as you can, because you'll need those for the rest of the year. Okay, so let's practice. Right? Once we think we might have learned all of our functional groups, now we really want to practice and see, can we identify the functional groups? Go ahead and pause it and do your best, and then come in and we'll go over it together. Okay, I am ready to go over it. So let's go ahead and do that. So you might have recognized this one right off the bat, right? So we have an aromatic, sometimes called an aromatic ring. It's a ring. And then this one might have confused you. Maybe you thought, oh, I see an amine, right? Or remember, with the CO double bond right next to the nitrogen, and the whole thing becomes an amide. And actually, this is another amide. Maybe you recognize that as well. The sulfur, because it's attached to carbon on both sides, is a sulfide. And then the last functional group that we have here is this one, where we have a carbon attached to carbon on one side, double bonded to an oxygen, and also has an OH group. That is called a carboxylic acid. If you labeled these alkenes, that is not correct, right? Because it's part of an aromatic ring, it's no longer considered an alkene. And just because you have rings over here doesn't mean that it's an aromatic ring. An aromatic ring has to be this 6-membered ring with alternating double bonds. Okay, let's talk about formal charge. So I told you before that sometimes it's possible to have a carbon atom with less than 4 bonds, right? When it does so, it does have a formal charge. Remember, carbon can never have more than 4 bonds. That's our cardinal rule. But it sometimes has less than 4 bonds. For example, 3 bonds. When it has 3 bonds, then it has a positive charge, and we call it a carbocation. A carbocation will have an empty p orbital. So each carbon that's a carbocation is sp2 hybridized with a steric number of 3. Each one is forming 3 sigma bonds. In this case, each one is to a carbon atom. In this case, there's 2 sigma bonds to carbon atoms and 1 sigma bond to a hydrogen, which is not drawn in. And over here, 1 sigma bond to a carbon atom and 2 sigma bonds to hydrogen atoms not drawn in. Either way, though, they are each making 3 sigma bonds to different atoms, and therefore they have a steric number of 3 and they're sp2 hybridized, which means they have the trigonal planar molecular geometry and the 180-degree bond angles that result from that. And then they have just what happens to the orbital that doesn't get hybridized, right? So if we're hybridizing to sp2, there's one remaining 2p orbital that does not get hybridized. That one is just empty. It's empty. The electron has been removed because it's an ion, right? It's a cation. And that means that that carbon is electron deficient and very reactive. It can react with things that are electron rich, and we'll learn about that later on. So it does have this empty p orbital, right? And that's something that it should you should be aware of. Okay, what about carbon with a lone pair? Is that possible? Yes, it is. It is possible for carbon to have a lone pair. When it does so, it will have a formal negative charge. The reason for that is the calculation, right? 4 valence minus 5 assigned equals -1. And so if there is a lone pair, it should be drawn in and you should show a negative charge, right, to imply that we understand there's a formal charge and that carbon is now electron rich and also reactive in a different way than the carbocation was. In this case, the carbon is sp3 because it has a steric number of 4. 3 atoms attached, right? 3 sigma bonds and 1 lone pair. So in this case, there aren't any p orbitals. All of the p orbitals were hybridized to form the 4 degenerate sp3 orbitals, and one of them has a lone pair in it, and the other ones are just one electron that went to form the signal bonds with the hydrogen atoms. So formal charge affects the stability and reactivity of molecules. So it's very important that we're able to identify formal charges in line structures. This particular structure is incomplete because it does not have the formal charges listed. So just like we calculated formal charge on Lewis structures, we should be able to calculate formal charge on line structures. It's really no different. Right? We just need to do our calculation. Number of valence electrons minus the number of assigned electrons will give us the formal charge, if any. So go ahead and take a moment, add in any missing formal charges, and then we'll go over it. All right, looking at this, maybe you recognize this oxygen atom with 3 lone pairs and 1 bond. Remember that oxygen typically has 2 bonds and 2 lone pairs when it's neutral. When you see something that's different than that, that should be like a red flag. Hey, there's going to be a formal charge here. There's 6 valence electrons on oxygen, minus 7 assigned, so this will have a negative formal charge. Nitrogen typically makes 3 bonds and has 1 lone pair. When you see it making 4 bonds, that means that it has a formal charge. The calculation is 5 valence electrons minus 4 assigned, which means the nitrogen has a positive charge. This one is neutral with 3 bonds and 1 lone pair. This oxygen is neutral with 2 bonds and 2 lone pairs. The sulfur, this is a bit tricky because the sulfur here has expanded its octet. Remember I said that's not super common and we're not going to talk about that a lot in organic chemistry. That's true, but sometimes you'll see it, and this is an exception. So we'll go ahead and calculate formal charge. Sulfur, just like oxygen, has 6 valence electrons. And it has 1, 2, 3, 4, 5, 6 assigned electrons. So it does not have a formal charge. What about this oxygen? Normally, again, oxygen makes 2 bonds with 2 lone pairs. So when you see it bonding differently than that, you know there should be a formal charge. The calculation here is 6 minus 5, which equals plus 1. So we put a little plus charge by it. And all the carbons here, because there isn't a formal charge already there, lone pairs, we can just assume that they are carbons with 4 bonds and no formal charge. And if there isn't 4 bonds already, then they have additional hydrogens bonded. Okay, so it is very important that we draw in formal charge because this formal charge means that there should be 7 assigned electrons, right? Because how do you get a -1 formal charge? Well, it has to be a calculation of 6 minus 7 equals -1. So in order to have 7 assigned electrons, we only have 1 for the bond, so we need 3 lone pairs for a total of 6 plus 1 is 7, right? So we can draw in the extra lone pairs. Of course, you know, oxygen needs an octet, so that's another indication that we should draw 3 lone pairs so that the oxygen has a total of 8 lone pairs around it. Let's look at some common patterns. But when you recognize common patterns, you just have to calculate less often. So for example, if I just recognize when I see an oxygen with 3 lone pairs and 1 bond, there's a negative charge, and I don't have to go, oh, it's 6 minus 7 equals -1. You just start getting used to the pattern. When oxygen is making 2 bonds and has 2 lone pairs, it's neutral. When it's making 3 bonds with 1 lone pair, it has a positive charge. So those are some common patterns to be aware of. Nitrogen also has some common patterns. Nitrogen in its neutral state will have 3 bonds with 1 lone pair. If it's making 4 bonds with 0 lone pairs, it will have a positive charge. And 2 bonds with 2 lone pairs will end up with a negative charge. The last thing I want to talk about in this part of the chapter is what it means when you see dashed lines and wedged lines. These actually indicate what the molecule looks like in 3 dimensions or in 3D. And it's difficult to do that on paper or a whiteboard because the of course, you're limited to the 2 dimensions of the paper or the blackboard or whiteboard, and you're trying to draw something that exists in 3 dimensions. So when you've probably seen this before, like for example, when you drew a tetrahedron, where you have groups on a wedge coming out of the paper at you, groups on a dash sort of going back into the paper, indicating the 3 dimensions. There's also hydrogens attached here because remember, each of these carbons has to have 4 bonds. So there's a hydrogen here pointing back and there's a hydrogen here coming out at you. Those are just not drawn in. So when you see dashes and wedges, just go ahead and recognize that those are groups either coming out or going back into the plane of the paper. And molecules drawn in 3 dimensions will be expanded upon when we reach chapter 5. There's some other ways to indicate 3-dimensional structure. You might see what's called a Fisher projection, a Haworth projection, or a bicyclic compound. Again, these will all be expanded upon in future chapters. But a Fisher projection is only used for acyclic compounds, and it's implying that these groups on the horizontal are coming out at you, and the groups on the vertical are pointed back. Again, you don't really need to worry about that right now. We'll come back to it when it becomes more important. A Haworth projection is an attempt to draw a ring, sort of not drawn completely up and down in 2D, but instead drawn this way, 2D, with groups either sort of coming above the ring or below the ring. And bicyclic structures are also very difficult to draw in 2 dimension. And so you can sometimes see that we will draw them this way, where we have 2 what we call bridgehead carbons, and then groups going sort of to the left, to the right, and above. Try to draw that. And then this sort of means that the group is coming up and down. And there's some 3-dimensional information that is conveyed in that bicyclic structure. Again, as we learn more about these, we'll come back to this. This is just sort of an introduction towards the 3-dimensional nature of structures. Okay, that's it for today. And go ahead and start working on the activity. And if you get stuck, take a look at that video key.